Okay, hello everyone. Thanks for joining us today at this co-located event. My name is Mengni, and I'm the Technical Program Manager from FutureWay. Very excited to share with you some of the exciting things we have been working on with our Centaurus platform. So Wenjing and Annie already set us a really good stage for today's topic, Metaverse. So my focus will more on the project itself. So here is the agenda for today. I'll first give you some overview of Centaurus, and then I'll talk about two Metaverse use cases that I can feel personally relate to. And then I'll talk about 4 projects with more details, and then I'll wrap it up with some takeaways and ways that you can be a part of our community. So as cloud becomes the norm to run current and future applications such as AI, 5G, Edge, Metaverse, and other emerging applications, we think that this new type of applications are driving the traditional cloud infrastructure to a more distributed cloud infrastructure. And we think the current cloud infrastructure needs to continuously evolve in order to meet the new challenges and requirements posed by this next generation applications. So we started building Centaurus, and it's an open source platform for building a unified and scalable distributed cloud infrastructure. We actually started working on smaller project in-house a couple years ago, I believe about 2019, and eventually put them underneath Centaurus and donated to Linux Foundation in December 2020. And as I mentioned, that Centaurus is a project umbrella, and it has a few other projects that we host underneath. And here are the few projects that are currently under our Centaurus organization. The first one is Octos. Is our open source project designed for a large-scale cloud compute infrastructure. It was evolved from Kubernetes with core design changes, and we can now support 50K nodes with our scale-out architecture. And Mizar is our high-performance and high-scale cloud network based on XDP program. And Fornext is our Centaurus Edge project. And Elnir is our AI platform, which aims to improve AI workload efficiency. Now that you have a better understanding of Centaurus and why we started the project, I want to share with you 2 Metaverse use cases that I can feel personally related to. Now, here's the first one is immersive meeting. As you know, ever since the pandemic, a lot has changed for many people. And for someone like me who have family that's not currently in the States, have family in China, so it has been very difficult for me to visit them in person. So to me, it will definitely means more for me. I would enjoy a catch-up that's more than just a phone call or a Zoom meeting. So a use case that I can feel personally relate to is meeting my family and friends across the globe in an immersive setting and watching TV together. So this way, I can talk to them, I can see their facial expression, and we can discuss the show together and maybe talk about the food we just had. Because for me, food really brings people together, well, in my culture at least. And now, because of this scenario, some of the use case for cloud that I can think of is, first of all, we have to have an underlying infrastructure that can really meet ultra-low latency. And the next one is network quality of service. Basically, there are some network traffic that's more important than the other. For example, if I'm talking to my family, it's more important that they can hear me real time and also see my facial expression, compared to if we're just looking at the VR glasses, the battery of our VR glasses, or if we're doing recording in the back. And another requirement is neural rendering. I will talk more in detail about the neural rendering, but basically is we can inference our facial expression onto the avatar in the Metaverse settings. So this is the first use case that I want to share with you. The next one is a healthcare use case that I find would be beneficial to the world once we're ready. And you can also see this as a virtual consultation. Basically, here's the scenario. I need to see my doctor who's living in a different city than me, and probably does not make a lot of sense to travel down to maybe California for the initial visit. So both of my doctor and I join a Metaverse session, and I can communicate with my doctor seamlessly. And with the help of AR glasses, my doctor can see my medical record by the display, since, it probably remember better than what I remember. I don't remember what treatment I have or more medicine I had from before. And another thing that the device can do for us is maybe tell the doctor how I feel. Is there any pain I'm feeling? and also my temperature, my blood pressure, just anything that you would do in a regular consultation. And with the help of AR glasses and the seamless communication, all of this together will make the process go smoother, like you're seeing in the background, like we're actually in the same office together. And how our project is able to help is to provide the underlying edge and networking infrastructure to enable seamless communication between two edge locations. And I will also talk more about that in detail shortly. Now that you have two use cases and some backgrounds about Centaurus, I would like to take you to the details of 4 of our projects. The right, Alcor and Mengni Zhang are our networking solutions, and Fornex and Elnir are our edge and AI solution. And I will start this with the Alcor and Mengni Zhang first, and then switch gear to our edge and AI. So, Alcor is a hyperscale cloud-native SDN platform, and it aims to manage the hyperscale of cloud network up to a few million hosts. Some of the challenge and motivation behind is that as more enterprise customers migrate their on-premise workloads to the cloud, the user base of a cloud provider could grow at a rate of 10 times in just a few years. So this will require a cloud virtual networking system with a more scalable and extensible design. So we started building Alcor from the ground up. Alcor is an open source cloud-native platform that provides high availability, high performance, and it manages large-scale virtual networking control plan and management plan at a high resource provisioning rate. And Alcor leverages the latest SDN and container technology, as well as an advanced distributed system designed to support the deployment, configuration, and scale out of millions of VM and containers. So on the right here, you will see a high-level snapshot of our Alcor control plan architecture, including the resource management service, infrastructure service, cache database service, messaging service, and the host agent. So the top 3 layers are our controller, and this is the messaging channel that will connect our controller with our agent together. So Alcor has a throughput optimal design, which focuses on top-down throughput optimization on every system layer, including the controller, the API, the messaging mechanism, and the agent. So then how do we achieve throughput optimal? So it's by horizontally scale our architecture. So currently, Alcor has 18 microservices. Each of them manage its own resource and scaling independently with its own database. And we're also doing profiling for our each of the microservices so it can perform even better. And with this architecture, Alcor can now horizontally scale out for 1,000 times scalability. And in addition to that, Alcor also supports batch and parallel network port provisioning for basically, we have a batch API to provide support deploying a group of ports with a single post call. And a message batching mechanism is proposed on a per host basis. So, which is we're able to drive in groups of resources to the same host with one shot. And that is the some highlights of our Alcor controller. Another thing that I want to highlight for the Alcor project is its ability to fast resource provisioning. So in order to support the time-critical applications, Alcor enables a direct communication channel from the controller to the host agent. So this channel bypasses a message queuing system like Kafka and utilizes gRPC to offer 10 times latency improvement compared to Kafka. And Alcor also have multiple control paths, including the gRPC fast path, MQ normal path, and the HA rescue path. Sorry. If an Alcor controller agent dies, a close-by agent can be the backup, and the host can still be up and running. With all of this together, Alcor is able to support fast resource provisioning with high availability and high reliability. And we also, and another highlight I want to share is from the Alcor agent. So it was built ground up with C++, which promotes high performance and multiple threading. And similar to Neutron DVR, we have our own Alcor distributed router, basically to enable host-to-host direct communication for L3 routing. Alcor distributed router uses highly efficient open flow rules, which eliminate namespace, links device, and IT table required by Neutron DVR. We also had a talk earlier this morning for the Alcor project, so if you're interested, feel free to check that out. And we also have expert in-house today that can have more discussion if you're interested. Next, let's move to the Mengni Zhang project. Mengni Zhang is our high-scale and high-performance cloud network. We built Mesa from ground up on top of XDP program. And some of the challenges that we think are current flow-based programming solutions are no longer suitable for the high-scale multi-tenant networking environment. Time to solution ports increase significantly as the number of ports increase. And also packet travel, so multiple network stacks on the same host, which leads to the latency. So again, we start building Mesa, and we build it on top of XDP. Mesa's main building blocks are XDP program that runs on each host. The programs implement virtual functions, including overlay switching, routing, virtual endpoint, load balancing, and more. And Mesa does have its own management plan, but for today's topic, I will focus on the data plan. So some of the highlights feature from Mesa is that it supports provisioning and management of large number of endpoints. And Mesa can achieve super low latency. I'm also going to share more data results shortly. And it also provides quality of service for different network traffic. And lastly, it's a multi-tenant network which enhances on the security. So traditionally, routing between VPC and subnet is managed by virtual switch and router. So this mandates that endpoints belong to the same subnets, and a network of endpoints must have a subnet address. And Mesa does not have that restriction. So Mesa introduced two new concepts called bouncer and dividers. They are in-network and horizontally scalable hash table that facilitate packet delivering between endpoints. Basically, the divider manages the communication between two networks, and the bouncer is in charge of the in-network packet delivery. So after the first hop of endpoints communication, the endpoint should be able to communicate directly between their hosting nodes without the need to go through the bouncer divider again. And we call that our first or direct path, which essentially allows a flexible data plane fast path that avoids multiple hops of flows through bouncer. And we were able to achieve great latency result with this architecture. Here is the latency result between Mesa with the direct path, Mesa with one bouncer, and the OVS path limiting break direct path and host to host, and it's round trip latency in milliseconds. So you can see that this actually has the highest latency with our for our bouncer with one bouncer. But even with the increased latency due to the extra hop, the packet per second processed by endpoint remains close to line rates. And after we enabled our fast path, Mesa's fast path latency is reduced to 0.14, which is better than the direct path from OBS and Linux Bridge at 0.16. Still a little bit higher than the host-to-host communication, but I think that just gives us more room to improve and grow. And that is the latency result. And here I want to introduce another features from Mesa, which is called the network quality of service. We also have a talk earlier yesterday about this, so you can also hear more later on. So basically what this is Mesa allows users to define their network traffic into 3 traffic classes: premium, expedite, and best effort. For premium, it's usually for real-time applications such as Zoom meeting or the immersive meeting scenario that I talked about earlier. For expedite would be like streaming video on Netflix or YouTube that requires some sort of bandwidth requirements. And for best effort, it's usually for data traffic such as file backup or email that doesn't really require a lot of QoS or zero to little at all. So with Mesa, we can provide, if we connect this back to our Metaverse use case, we can label the real-time conversation and our facial expression as the premium traffic. And we can label the recording in the background as best effort traffic. And that will still make the experience feel seamless, and we can see each other's facial expression, and we can talk in real time. And as I mentioned, we have a talk regarding to this. If you want to hear more, feel free to check that out after the recording is available. And that are the 2 highlights I want to share from the Mesa side. Next, let's switch gear and talk about some of our edge solution called Fornex. Fornex is an autonomous and flexible edge framework. It provides a framework that allows users to run reliably in the edge environments. And some of the key edge computing challenges that you're probably already very familiar with is first, we have limited computing resource at edge sites. And next is the heterogeneous resource type. Might have unreliable network or long latency. So we really want to offer a way for different components of application to run in their best suited environment with collective efforts. So we want to introduce to you our Fornex project, an autonomous and flexible edge framework. Why is it flexible and autonomous? Because we offer different ways of organizing these clusters. So you can choose how you want to manage this cluster, and you, as the user, will make the decision. Basically, we introduce two modes. First one is a single layer mode. This way, there's a cloud control plane and there's the edge cluster. The user has the freedom to manage their edge cluster directly from a cloud control plane, which could be Kubernetes or lightweight Kubernetes or a solution from Centaurus, the Octo solution. So the user gets to choose if they want to manage their edge cluster directly from the cloud control plane. And another option that I want to introduce to you is our hierarchical edge cluster. So in this mode, information does not need to go through the cloud. So in this picture, you see there's a cloud control plane and there's a few edge cluster. And they are structured in multi-tree-like topologies. So please know that we're actually talking about edge cluster here, so we're not just talking about edge nodes. And each of this edge cluster will have their own management plan, so they can manage on its own. So what benefits does this topology have? So first one, geo-localized resource allocation and management. Basically, we can decide where we want to put our applications, of course, to as close to as where we are physically as possible, so the latency can be guaranteed. And another benefit would be flexible architectural choices. Basically, if the user want to go into the cloud control plane and manage everything from the cloud, they can have the freedom to do so. Or if they want to go into one of the cluster, whether it be edge cluster A or edge cluster A1, they can also do that. And another benefit is autonomous local management. Basically, since we're managing edge cluster here, if one node fails, the management plan is able to manage the failure and start another node, or they can help with routing the traffic. And lastly, since we are just sending lower load of traffic onto cloud control plane, we're really cutting down the latency and the overall cost of management. And another important feature from Fornex is our edge networking. Basically, it's a multi-cluster, multi-tenant edge cluster networking, which supports concepts like VPC and subnet with the help of our Mesa project. So basically, currently in Mesa, the project that I quickly talked about earlier, is we can already support cross-subnet communication. So a pod can talk to a pod in different subnet as long as in the same cluster. And with Fornex, we're able to take this a step further. Now we can achieve inter-cluster communication. So for example, for pod 1 in subnet 1, they're able to communicate with pod 2 in subnet 2, despite they're in different edge cluster. And here's a high-level picture on the right here. So C1, just think of this as a cluster. C1A can communicate with C2A, even though they're different cluster and they're in different subnets. And with this, we can tie this back to the healthcare virtual consultation scenario where patient and doctors are in two different edge sites, but with our help of our edge framework and on the networking framework, we can make sure that the two locations can communicate with each other with no latency, with very low latency. And that is our edge project. Now let's on to the last one, is our Elnir platform. Elnir is a self-learning platform to improve AI workload efficiency. And our goal is to accelerate AI training across multiple layers of AI stack. Some challenges that we're currently trying to tackle is, first of all, data loading. How to load data fast due to limited network bandwidth. Basically, from our experience, we think that network is usually the bottleneck, so we want to work on how to load our data fast. And another challenge is, since we're trying to improve the AI training workload efficiency, we need to first identify where the bottleneck is. So we have our Elnir profiler. This profiler, we implement our own profiler to do cross-layer profiling and data correlation so we can identify where the bottleneck is. And the next one is fractional GPU sharing. Basically, there are some inference jobs such as translation or image classification that we think do not need the entire GPU. So we want to support fractional GPU sharing in order to improve the GPU utilization rate. And lastly, we want to enable RDMA fast network over TCP/IP in order to reduce the times of copy. And that is some of the challenges that we're trying to address. And here is the high-level architecture of our AI stack. In the top layer is the emerging application layer, where we work on neural rendering. It's the rendering method I talked about in the very beginning related to the Metaverse use case. So neural rendering, based on some existing image, we can generate novel views of a person. And the next level is the ML framework. So in the ML framework, we have a cache manager, which leverages the in-memory storage to catch the training data. So when we do training, it can be faster. And another thing in the ML framework is the LNAIR Elastic framework. Basically, instead of using one machine, we want to use multiple machines to train. And in the third layer, we have our container platform. Basically, we have a CRD controller platform. We have our own LNAIR job and LNAIR pods. So when you deploy training jobs, you can use our LNAIR jobs, and our controller will take care of all the resource management. And at the very lowest level is our hardware. We have our own GPU and our network plugin to make the whole entire infrastructure fast. Now here is the first highlight feature of LNAIR, cross-stack profiling. This is how we identify training bottleneck. So we have our LNAIR exporter and a LNAIR profiler. And in the exporter, we export data. We collect data at different levels, on the GPU level, the CUDA level, and the Python level. And then we extract those data into our time series database Promisue. And then our LNAIR profiler will do all the data aggregation and data analysis. That's where all the AI capability is. And in order to achieve this, we need to insert an LNAIR intercept library into the user pod so we can extract all the data. We follow a top-down zoom-in job completion time to identify application performance bottleneck, and we store pod metadata and execution data in a structured way for cluster performance analysis and learning. And that leads to us to our next feature. It's called reinforcement-based GPU scheduling, considering job interference. Basically, this is how we do GPU sharing and how we improve our algorithm. We'll first collect the key metrics for each workload, including, say, GPU utilization and memory utilization, and we'll do clustering. After that, we'll have a knowledge base. We know what job pair will perform better together, and based on that, we'll do a dynamic scheduling scheme. And we'll run those clusters and see how the job completes, basically how long it takes and whether it is a good pairing. So whether it is a good sharing strategy. If it's a good sharing strategy, we'll continue to enforce it. If it's not, we just do different randomization. So we generate different schedule recommendation. In this way, we're constantly learning and dynamically improving our scheduling algorithm in the real environments. Now, the last features, I think is also one of the more exciting features for today's topic, is the neural rendering. Basically, based on existing image, we can generate novel view of a person. Let me see if this plays. Oh, it's not playing. Okay, yeah. Based on existing image, we can generate novel view of a person. So we actually have a demo in-house that focused on this, and this is not the actual output, but I can share more with you on the demo if you're interested. And on top of generating novel view of the person, we can also check the real person's real-time expression and inference that onto the avatar. So if we ties back to our immersive meeting scenario, this will allow our avatar to capture our real-time facial expression and our friends can see. And this is currently one of the hottest and challenging neural rendering algorithm in the community, and we were able to implement it to LNAIR and have API ready for you to call. So that actually is all the project I will be talking about today. Just to refresh your memory a little bit, we have our LNAIR AI platform, our Fornex Edge platform, our Alcor control plane, and our Mesa data plan. Some takeaways is that for LNAIR AI plan, we implemented one of the hottest neural rendering algorithm, which allows facial expression inferencing onto an avatar. And for our Fornex Edge platform, we if they're in the same VPC, we enable edge-to-edge communication, which help with the virtual consultation scenario. And with our Alcor control plan, we can support large-scale network provisioning. And with our Mesa data plan, we can provide very ultra-low latency and also network QoS features. So we think that with the underlying edge and networking infrastructure, we can really help with the metaverse scenarios. And again, as I mentioned in the very beginning, our cloud environment really needs to continuously evolve to meet this next generation application. So I also want to share with you some of our next step, actually also our current step. We're currently transitioning to Centaurus 2.0, and there are 3 major components that I want to share with you today. The first one is called Centaurus Regionless Computing Platform. Basically, it's a new model to use cloud, from resource-based to application-based. Our goal is to manage 2 million compute nodes from big, small, edge data center as global resources. And we currently have 2 repositories under the Centaurus infra repo that are dedicated for this components. Feel free to check those out. First one is Global Resource Service. The other one is Regionless Storage Service. And the second component is Centaurus Edge Serverless Platform. Basically, we want to have a platform that can support extremely low latency, less than 100 milliseconds, for starting application instant at edge and auto scale to handle burst requests. And the repo for that would be Fornex Serverless. And lastly, we also have a Centaurus Container Runtime Engine. It's a high performance and secure container runtime with better throughput and lower memory overhead compared to gvisor and Kata. And that is our open source project Quark. Feel free to check those out. And with that, want to wrap up my conversation. So for today, it would be great if you can leave this talk telling 2 or 3 friends of yours about Centaurus. Visit us at centaurusinfra.io. Check out our website from GitHub pages. There are 2 links right here, Centaurus Infra or FutureWay Cloud at Alcor. Basically, I really encourage you to check out our repository and leave an issue in the announcement section or the discussion session so we can really engage you with the right people. And lastly, feel free to join us at our Google group to be a part of the community. Thank you guys. That's all for my talk.